Okay, well, it's a real pleasure today to introduce Chris Greene, who's going to give a talk from the University of Colorado. That's me, as it turns out. And the subject for the discussion I wanted to present today relates to universal physics, which is a rather fascinating field to me in that it addresses topics that span many orders of magnitude in different fields. All the way you're getting insights into nuclear systems at MeV kind of energies, and all the way down to sort of nano electron volts in ultra-cold quantum gases. Most of the experimental interest is coming more from the side of ultra-cold gases, and that's part of the real excitement in this field, is that after several decades in which theorists were really doing almost all the work in this area related to Efimov physics, I went ahead and started without you. Now experiments are contributing and really adding to the fun. So my work is at GILA. This is NSF-supported research. And the work was done by 4 talented co-workers, 2 postdocs, Nirav Mehta and Jose Diancao, and 2 graduate students who've now gone on to bigger and better things, Javier von Stecker and Seth Rittenhouse. To this general area, my interest in this general area, also Brett Esri and Dorte Bloem have made some important contributions and collaborations over the years. So this is just showing one of the highlights last fall, the first sort of real meeting where Efimov-related 3-body and 4-body physics was finally seen experiment that actually confirmed a lot of Efimov's early ideas dating all the way back to 1970 that had gone for a long time without any experimental evidence at all. He's giving a high five to Randy Hewlett, one of the experimentalists who verified some of his predictions. So in this particular talk, I want to convey our picture of how we go about treating a few-body collision problem with multiple particles in the continuum and, in some cases, bound states and resonances coming into play. Our favorite picture is using hyperspherical potential curves to depict the pathways. There are other methods that I'll point out that have derived largely equivalent results. And in particular, focus on our latest theoretical work that I was very excited about. We were finally able to describe a 4-body recombination process, non-perturbative process involving 4 free atoms that collide and form either a trimer in an atom or two dimers. So if you like to think, again, this is universal physics, so it applies whether we're talking about nucleons in a nucleus or atoms, or it could be molecules in certain energy ranges of collisions. If you have 4 such free atoms in a gas, they can simultaneously come together, and like this cartoon shows, they can collide and exchange energy in a way that ends up forming 2-body fragments that then break apart. It's maybe more common to think of a 2-body collision where 2 dimers collide and blow everything apart, but even that's a fairly rare process that has only rarely been treated by theory. We've been focusing on the time reverse because that's the important loss process, especially in Bose-Einstein condensates. More for 3 bodies, that's been known for since the mid-90s, that was the dominant loss process because experimentalists had found really clever ways to turn off the bad 2-body collisions that would flip a spin of an atom in one of these dilute Bose gases. But this cleverness couldn't also at the same time turn off the 3-body bad losses. And now we'll see some regimes where even 4-body loss is dominant. So I was looking at some of the talks on the KITP website, and you see different methods to treat scattering theory. This one by Byrne at UCLA, where if you try to go with these methods that are kind of starting from a perturbative point of view and adding Feynman diagrams, there are lots of challenges and difficulties, and it may be that you could represent a process with 3,017,489 Feynman diagrams. It would be hard to look at that set of 3 million diagrams and pull out some real, key insights. Maybe a few would dominate, but that's what you would hope for. But what we're trying to do is develop methods that not only are an efficient way to do the calculation for these few-body continuum processes, but also which will really pinpoint the qualitative insight in physics and give an interpretation. So for this particular colloquium, I want to review tunable two-body scattering lengths, which has been a subject that has revolutionized ultra-cold science. The ability to have a Fano-Feshbach resonance whose energy depends on magnetic field, so that you could tune it right down to zero energy and make the scattering length of the two bodies go to infinity. And really have a knob in the laboratory that you could sweep. And this has been really interesting to have many-body Hamiltonians and few-body Hamiltonians with a knob on them, with a parameter that's adjustable in the laboratory. And this has been really the key that led to the observation of the Efimov effect in 2006 for the first time. Our systematic framework I want to discuss for treating non-relativistic collisions, with n particles, a fixed number of particles. And we will be using this adiabatic hyperspherical picture that I will describe in a few minutes. I think it could be more broadly applicable than to these problems in chemical physics that we've been applying it to, but I haven't really seen methods like this used, for instance, in high energy physics. Of course, there you have other problems, the creation and annihilation of particles and things like that. I'm not sure this method handles those issues seamlessly. But anyway, there is some exciting progress now in 2009 and 2010 with experiments and more theoretical work. Now there's four-body, the extension of four bodies interacting into the universality regime. And I'll summarize with some of the prospects recently to treat more than four particles. So our kind of general motivation, I would say, what we're trying to achieve is to understand how multiple component quantum systems fragment and collide and do all the interactions they do, and see what kind of interesting properties and relations come between bound and resonance states, and also see how to, what regularities emerge from the collision physics and the scattering matrix. This is all non-relativistic quantum. Of course, we're ultimately going to be calculating the scattering matrix, and in many cases we need to use the Born-Oppenheimer approximation or its generalizations to the hyperspherical radius. And speaking of hyperspherical coordinates, these have been used over the years. One of the earliest papers I know of that used it was Thomas in 1935. This is L.H. Thomas, the same one who derived the Thomas precession effect. He had an important paper in nuclear physics I'll talk about later. And so, for instance, if you had in chemical physics, for instance, a collision of two diatomic molecules that forms a complex and then can fragment in multiple different ways, this is still really beyond the state of the art of physical chemistry to calculate the process, even if you are given the potential surface, except in a very small cases, mostly having at least 3 of the 4 atoms being hydrogen atoms. So ultimately, I hope that these techniques will pay off to be able to solve problems like that. In particular, in our 3-body recombination process that we'll be talking about, you have 3 atoms in a quantum gas, maybe at 1 or 10 nanokelvins temperature, and they're going to collide and form a dimer with some binding energy. This dumps enough kinetic energy into the fragments that they're all ejected from the trap, typically. We also have applied some of these methods to dissociative recombination, another four-body problem, but I won't talk about that today. Okay, so these look probably on the face of it like really complicated systems. If you imagine 4 rubidium atoms or cesium or lithium coming together in a gas and doing all this complicated interaction, and you might imagine whether there will really be some simple things come out of it at the start. When we began this, it wasn't all that clear. But in fact, some nice simplifications and simplicities do emerge. So the reason we call this, let me start with universality. The reason we call this universal physics is that you have we're talking about systems with finite range interactions between all the particles, and there's one big length scale in the problem, and that's the particle-particle scattering length. If all the particles are identical bosons, all these scattering lengths are the same for every pair of particles, and that's one limit that we're especially interested in. But of course, sometimes there are multiple components. Sometimes we apply these ideas to Fermi systems and so on. But except for these changes in symmetries, the common physics is this one dominant length scale of being the scattering length. And then having said that, there will be some characteristic range of the interactions, and we're interested in scattering lengths larger than that. As long as you're in that regime of maybe 5-10 times larger than the true range of the potential energy between the particles, we call this the universal regime. And once you're in that regime, the properties I'll be talking about are applicable either to nucleons or atoms, clusters, and so on. So, and this has been a nice unifier also for theorists, because then it kind of brings high energy and nuclear, condensed matter, and atomic theorists all kind of talking at the same conferences, and there's been a fruitful exchange of methods tackling these problems from very different points of view. Okay, so first let me just kind of give the sketch the way we like to think about it with adiabatic hyperspherical coordinates. Imagine an n-particle non-relativistic quantum system, fixed mass is mi, and positions ri. I'm thinking of these relative to the center of mass of the system so that this trivial degree of freedom can be removed. And then if you write that in terms of a single length scale, the hyperradius, which is, you can think of, its square is proportional to the trace of the moment of inertia tensor. This is a general coordinate you can define for any number of particles of arbitrary masses. And it's interesting and useful because the kinetic energy then separates in these coordinates if you define this one length, and all the rest of the coordinates of the system become angles, or we like to call them hyperangles, that represent the motion on this hypersphere in arbitrary number of dimensions. So our Hamiltonian that I'm interested in just has the simple structure of a kinetic energy plus a local potential energy. Usually it could be generalized to non-local, but we normally don't have to do that. And then the kinetic energy has a form with d by dr terms, kind of what you're used to seeing in an arbitrary d-dimensional system. And then there is a hyperangular kinetic energy term that is related to the OD group and the generators of that group, the Casimir operator in that group that defines something like, you might think of it as a generalized or a grand angular momentum on the hypersphere, including all the hyperangular motions. And of course, hyperangles means that not only true physical angles of particles are changing, but also the ratios of distances are changing as you move in different areas of that hypersphere. And well, this has a well-known set of harmonics on this hypersphere. The angular solutions are called hyperspherical harmonics. There's a complete orthonormal set, just like for spherical harmonics. And you can symmetrize those if you have to enforce Pauli symmetry for fermions or Bose symmetry for bosons, whatever symmetry group is relevant. Okay, so now if you think of solving the time-independent Schrodinger equation to describe a stationary scattering, time-independent scattering wave function, you can expand in principle into a complete set of hyperangular functions. We like to pick not the hyperspherical harmonics like a lot of people do, which really don't have much physics in it, because it's just like spherical harmonics don't have so much physics in it in a sense, although they're very convenient. But we like to go through this intermediate step of first diagonalizing the fixed R Hamiltonian. Okay, so it's just like the Born-Oppenheimer method in representation, basically, except the hyperspherical radius is playing the role of the adiabatic coordinate instead of an interparticle, internuclear distance, like in molecular physics. In principle, you can do this. This is a Hermitian Hamiltonian. It has a complete set of eigenstates and eigenvalues that are parametrically dependent on R. And we think of these as adiabatic potential curves in the same way as Born and Oppenheimer. And so if we can diagonalize this operator, which may be very hard, and in fact that is the bottleneck in many of our calculations as we try to go to more particles, but if we can diagonalize this, then it reduces the whole problem, this d-dimensional partial differential equation, it reduces that to an infinite set of coupled one-dimensional equations, which at least I find easier to visualize, seeing a set of simple potential curves. And you can identify then collision pathways along those potential curves that lead to different reaction outcomes. In some cases, people even drop all these coupling terms that drive transitions from one potential curve to another. This is called the adiabatic approximation. But the phenomena I'm talking about today really require these, and these transitions are at the heart of what we're trying to really describe. Okay, so let me remind you just a few of the basic properties of two-body scattering lengths before we start talking about three-body physics. Of course, the scattering length should be the limit as k goes to 0. I don't know why I wrote n goes to infinity. I have no idea whatsoever. But never mind that. It's the zero energy limit of the negative S-wave phase shift divided by the wave number, of course. And remind you another property of two-body interactions. If you have an attractive potential in one dimension, no matter how weak it is, it still always is guaranteed to have a two-body bound state. Any potential of this shape will be guaranteed. And this is a problem I often assign in my beginning quantum courses to prove this. It always has a two-body bound state. But 3D is different. In 3D, you have to lower the potential well to a certain minimum amount in order to bind two particles and have a bound state at an energy below zero energy. And I have a short animation showing how, as you vary the potential well, the scattering length changes. So this is a potential well for two bodies, two S-wave particles, two particles with S relative wave. And the scattering length, as I'll change the overall constant in front of this from repulsive, where it is now, it'll get negative, and the scattering length will change from positive to negative, and then go through this pole. Okay, so this magenta dot is changing the scattering length, and this is what the potential looks like when it's at 0. For some reason, this animation stops sometimes. Let me try it again. And when it hits 0, the potential is 0. Okay, there's no interaction. And then when it's negative potential and small, it's a negative scattering length until you reach this point, at which point you have the first bound state going through 0 energy. And at that point, the scattering length diverges to minus infinity and reemerges from plus infinity, and you have one bound state in the system then. And if you keep making it deeper, there will be another pole where you have two bound states, and so on. Exactly, yeah. The Wigner threshold law guarantees that the lowest partial wave allowed by symmetry almost always dominates.
So you make this.
Yeah.
You're always
That's right. That's a good point. I mean, sometimes we do go and look at P-wave physics when S-wave is excluded, like for a gas of 3 spin-polarized fermions. But I'm not talking about any of those cases today. Big difference in what? Oh, yeah. Well, that's right. Well, high energy physics also, if you're just above a threshold, then the threshold laws will still kick in. Okay. So now let's talk about the Efimov effect. Okay, so within that framework of trying to make these hyperspherical potential curves, Efimov didn't state it in that language, but in effect that's what he was doing. You can, map his paper onto this method, which was really this adiabatic hyperspherical method was invented, I would say, by Joe Masick in 1968 paper. Anyway, if you solve that, you find, in fact, it's exact for this problem. If you have 0 range interactions and you can solve for this adiabatic hyperspherical potential curve, and you find exactly it has the form of a 1 over r squared attractive potential. If you go, I'm sorry, I didn't say the most important thing. This is if you go to infinite scattering length, infinite two-body scattering length. In that limit, you have this attractive 1 over r squared potential. I like to think of this as an effective dipole potential. What I mean by dipole is that the charge interaction with a dipole moment is a 1 over r squared attraction also. And so in that sense, this maps onto what we know from other AMO problems I've worked on, where you have an electron, say, in the field of a polar molecule or any polar system. But yeah, that's what I mean by a unitarity. And George Birch in nuclear physics has called this the unitarity limit in interaction problems between nucleons. Okay, so, well, if the potential energy of the system is the simple 1 over r squared, you can imagine you can solve that radial Schrodinger equation exactly in terms of Bessel functions. They're slightly weird Bessel functions because it's a negative, which means they have imaginary order. But that's not such a big complication. It can be done, and all their properties are quite simple to work out. And the most important property that Efimov predicted is that you have an infinite number of bound levels in such a potential that converge geometrically. Each successive level is a constant factor closer to 0 energy than the one before. And this constant factor is universal. It's very close to unity if you have 3 identical bosons of the same mass there, because they're identical, it's guaranteed. But for 3 identical bosons, you get this factor very close to 1. For other systems, this number changes. And this number, in the case of 3 identical bosons, this exponential factor is approximately 1 over 515. So each successive level is 500 times closer to 0 energy, but there are an infinite number of them, just like in a Rydberg series of levels in electron in an atom. Well, you can see this, for instance, this is following a general rule. Coulomb potential has energy levels going like 1 over n squared, an infinite number, and their radii spread out like n squared. The principal quantum number n squared. Charge dipole interaction, like we have in the Efimov problem, even though all these are neutral particles, but the math is the same as for charge dipole. You have this geometric scaling of energies towards 0, and the radii are expanding exponentially as you go to higher and higher quantum numbers in the potential well. Okay, now another oddity about the Efimov potential curve. This.
In real life, this is cutoff.
Yeah, that's. In fact, I'm just getting to that. Exactly. At short distances, yeah. But in fact, yeah. This addresses that point. There are really for this 1 over r squared potential, there are two infinities. There are an infinite number of levels arbitrarily close to zero energy, and the ground state energy is also arbitrarily deep. In every physical problem I'm aware of, the infinity, the very deep bound state, ground state, this is cut off by the fact that the dipole potential doesn't really hold all the way to the origin. But it still is interesting that Thomas predicted this effect in 1935, where he looked and he assumed some scattering length between the nucleons was known. And he showed that if you make the range of interaction of the potentials arbitrarily short, the potential well had to get arbitrarily deep, and that the 3 nucleon energies would follow that depth and get arbitrarily deep as well. And so by that analysis, he was able to actually estimate the size or the range of the nuclear forces. This is kind of a cartoon. If you work this out for a square well, for instance, you can derive the exact scattering length, S-wave scattering length, for a square well, which just has this tangent function. And if you go to the limit where A is much larger than R0, then you find the well depth gets deeper and deeper, like minus 1 over R naught squared, the range. And the 3 body energies are going to be of that order of magnitude. And so by knowing the actual experimental 2 nucleon and 3 nucleon binding energies, he was able to deduce the approximate range of the nuclear forces. Well, I think it was just right in the ballpark of a Fermi. I don't remember the exact number. There's also some uncertainty because there are different scattering lengths between the different nucleons, of course. So another way I like to kind of phrase the weirdness of the Efimov is that you're imagining having 3 particles and each pair of them doesn't bind. Okay, but it's infinitesimally close to binding. Okay, so think of approaching this from the direction that the scattering length is close to minus infinity. So none of the 2-body subsystems are bound, and yet the 3-body system has an infinite number of bound states. Now, the first time I heard that, when I was a graduate student at Chicago working with Ugo Fano, I was really pretty dumbfounded. I thought this was just too bizarre to be imaginable, that even if you had no 2-body subsystems bound, you could have an infinite number of 3-body systems. And later, when we decided to study this in the 90s, my initial idea was, well, this probably isn't true. But anyway, we, like other theorists, ended up confirming it. When you really go through the theory, it really does hold. And there is really this infinity of bound states, even if you have finite range potentials, even if you don't go to 0 range limit. Okay. And so, for instance, Efimov, whose main paper was in 1970, he even suggested Yeah, that's right. Yeah, that also would be cut off. Well, but now we can tune it. In these cold gases, we can tune it really to the infinite point. I mean, of course, it's cut off by the harmonic oscillator trap and all the other stuff. Yeah. So in practice, it's always cut off by some physics, but still, you could have a very large number of states. Well, I think the largest 2-body scattering lengths in the ultra-cold gases are around 10,000 Bohr. Okay, so anyway, Efimov looked at the triton as a candidate for this type of physics. And if you go through the estimate, the expected number of Efimov states, if you have a finite scattering length now, it depends on the logarithm of the scattering length divided by the range of interactions. And if you take the known scattering lengths and sort of take some average, you get a number of 0.9 to 1. So from that point of view, you could say it's maybe a semantic game that the triton is an Efimov state. Okay, but again, it's just a semantic game. You have no control over the Hamiltonian, and there's no real implications one could really explore from that. It really, Yeah, that's right. Well, the Efimov effect does extend on both sides of this pole to varying degrees. So yeah, you need the absence of a bound state to at least say you're studying this universality Efimov regime. Okay, so coming back to this hyperspherical approach that we're going to use to tackle this problem, one could view this a little bit as a divide and conquer strategy that somehow we want to get those potential curves, okay? And it's maybe not so interesting how we do it. Sometimes we use finite element methods. Sometimes we use Gaussian basis sets. Sometimes we try to use other basis sets. But it's kind of like the way I might approach a reactive scattering in physical chemistry. I want someone to give me these potential curves and couplings, and then we can study the dynamical mechanisms, the potential barriers, and see what is really the physics. But once you have those, it's pretty smooth sailing. Okay, so there are some systems we've applied this to, like 4 atoms in a degenerate Fermi gas is one interesting one, where as you sweep the scattering length through the pole, you go from the BCS side, where you have no two-body bound states, to the BEC side, where you have a boson condensate of molecules. And this is one system. Again, I won't really present any of our results for that system today, but you can look at it that way. There are other 4-body problems, again, like this one with H3+, I won't discuss today. But let me at least kind of show you the landscape, the way it looks once you can calculate those potential curves. And this is one of our early calculations for 3 helium atoms, ground state helium atoms, interacting with the best known potential surface for these atoms. And this is what they look like. And one nice thing is that you can see at infinity what the system is fragmenting into just by looking at the energy and other quantum numbers that it fragments into. In this case, helium dimer is known to be very, very weak. I forget the actual number.
These potential curves can't be viewed just as like you look at this, you can't just think of this as one mathematical problem with potential.
Well, there's coupling, yeah. You don't see in this graph the coupling between them. But still, that qualitative intuition still roughly works.
That's a question.
And I mean, that's... Right, and we have calculated, for instance, in the adiabatic approximation, there are 2 trimer states in this lowest potential curve, and they're within 10% or so of the real energies that accurate calculations give. And a number of other cases. I should say there are cases where this adiabatic approximation fails impressively. More typically, in my experience, for asymmetrical systems, like if you had 2 heavy particles and 1 light, then this adiabatic hyperspherical, the couplings are much stronger and it doesn't work as well. But for a symmetrical system, like with equal mass particles, it seems to work quite well. Yeah, Zach?
For a non-symmetric system, is that because you're not getting the curves very well, or the couplings, or just because the coupled channel problem is not?
No, it's really the coupled channel problem. We can really nail for 3 bodies now, we can really nail the problem of getting the potential curves and couplings. So, in fact, through this and also through things like Landau-Zener type analysis of couplings and so on, we found that you can really think at a qualitative and semi-quantitative level of these just the way you think of potential curves in molecules. So again, the physical meaning of this fragmenting this lowest curve, it has to go to the ground state of the helium dimer, which is just barely bound. You can hardly tell it's below 0 over here, but it is below by something like 1/10 of a milli-eV or something like that. These other potential curves all converge to 0 energy, and they represent an infinite number of channels of the 3-body that span the 3-body zeroing momentum continuum, where all 3 particles are free. And so in that picture, we can describe what a three-body recombination process looks like in a helium gas. It's simply a collision where you come in on one of these channels at low energies. You'll be predominantly coming in on the lowest channel. And it will have to tunnel into small distances where there's an interaction, a non-adiabatic interaction, and jump into this other curve and fragment, dissociate off to infinity in that lowest channel. So it's very intuitive then how these reactions occur. We did this calculation, I think that one was published in maybe around 2002. And the first real independent check of that came out of a paper by a nuclear theorist in Colorado, Jim Shepard, in 2007, who developed an independent treatment using separable potentials and Fadeev treatment in momentum space using our same Hamiltonian, and he gets, you can see, quite good agreement with our predictions. So there's still no experimental measurement of this for helium, but seeing a graph like this gave us a lot of confidence in our own method. Some of the phenomena you see in three-body recombination now as a function of the two-body scattering length are shown here that we mapped out in some of our systematic studies. And we found that there are always infinite number of shape resonances of Efimov character at large negative scattering lengths. This is the first, and as you go up by a factor of 22.7, you'll keep seeing more and more of these three-body recombination resonances that are really Efimov states that have merged into the three-body continuum. And another thing that we always thought would be more interesting to experimentalists were a series, an infinite number of destructive interference minima, where you could turn off three-body recombination by setting your scattering length to these special values. The way we could interpret those minima is in what's known as the Landau-Zener-Stuckelberg picture, semi-classical picture, that you can think of coming in a three-body recombination process, coming in with your three cesium atoms, in this case, on a three-body channel, and then you can jump on the way in, following this blue path, onto the two-body fragmenting channel, and then not jump on the way out. Or you could come in and not jump on the way in, but jump on the way out. These two have a characteristic phase. It depends on energy and scattering length. And there are regions in both energy and scattering length where they have a destructive interference. And those two pathways exactly cancel out. And so other calculations have since verified that these minima are in completely independent methods. If hyperspherical coordinates is not your cup of tea, then there are other methods. Broughton and Hammer have a series of papers using low energy effective field theory method to derive many of the same results we have in a quasi analytical treatment. Jim Shepard's method I just mentioned. There's also a nuclear theory method developed by Sandhaus, Alt, and Grassmann back in the 1960s. This was applied in 2007 by Kuhler and Lee and Julien, and also got some solid results for cesium recombination. Then there are model treatments. There is a high-energy theorist in Heidelberg who uses functional renormalization, and they've also been able to derive some of these, reproduce some of these results. And for instance, some of the things that come out of the Broughton-Hammer work is starting with an effective field theory Lagrangian. They can derive a formula like this that has the log periodic dependence on scattering length of these resonances and so on. Okay, so those are maybe just a few more details and other references you could look at. I know they went by kind of fast. I can give anyone who's interested the full references later. So the first experimental evidence, people had looked for these Efimov signatures for many years, even dating back to the 70s without success. But finally in 2006, Rudy Grimm's group in Innsbruck was able to measure three-body recombination as a function of scattering length in cesium and see a resonance that looked very much like what we had predicted in 1999 that had Efimov character. And this was the sort of the link, this link to theory was what gave pretty strong evidence that what they were really observing was, for the first time, an Efimov state. They saw a little suppression here, but not enough to really look very much like our predicted minimum. So that was, I would say, not really confirmed, although there was some suggestion that there could be a minimum at positive scattering lengths like we predicted. Now, in 2009, suddenly there has been an explosion, and continuing into 2010, many different experimental groups, I think around 10 or 15 experimental observations of Efimov physics. This was one of the more impressive ones published about a year ago, I think in potassium, where they now have seen the clear minima at positive scattering lengths, and they are separated in scattering length by this factor, this Efimov factor of 22.7, this expected scaling. They also see resonance at negative scattering length, also consistent with what was expected in our theory and other theories. So let me just go on then, because it started to look, especially after 2006, like the three-body problem was getting to be fairly well understood. We decided to dive into the four-body problem and see what universal physics could be there. And, well, here's a series of papers again. You can see them. There are both numerical treatments with realistic two-body interactions, and we also have a more analytic theory within the zero-range limit that is useful for doing more analytic work with Greene's functions. Okay, so this is really the question we wanted to address. To what extent does Efimov and universality physics have some relevance for the four boson problem? There was some previous work I wanted to mention, in particular by Hammer and Platter, who conjectured on the basis of their effective field theory studies that there would always be two four-body resonances lying in energy between any two three-body Efimov state and energies. There was some corroboration in some work by Dörte Blum on some of these points. But we went ahead and just did the calculation, pretty much our own way, not paying too much attention to that. And this is the energy spectrum we got as a function of inverse scattering length. Okay, so if you want to think as you move from left to right, you're making the system more attractive. This is the universality point, A equals infinity, where 1 over A is 0. And on the other side, you have two-body bound states, either one dimer or two dimers. So on this scale, you have the infinite number of Efimov states at infinite scattering length, shown in green. And these are the energies we found for the tetramers. And in fact, it basically does confirm that in the universality limit of large scattering lengths, we do find two four-body bound states between, sort of attached to and slightly below each trimer, Efimov trimer. Now, while this confirmed the conjecture, one thing that we did that went beyond that was to look at the experimental observability of these states by coming over here to where they merge into the four-body continuum, where they should show up as scattering resonances in a four-body recombination process. And in particular, sorry, I should mention this is not a linear scale. It's sort of like a logarithmic scale in this scattering length axis. So in fact, these 2 points occur, that one tetramer state is at 0.43 times the three-body resonance value of the two-body scattering length. And the next one, the second tetramer, is at 0.90 times, that's what we found, times the 3-body Efimov trimer. At those special values, no matter what else is going on in the Hamiltonian, you should see some signature of this in the 4-body recombination signal. And this is what the 4-body hyperspherical potential curves look like. Very simple, in fact. They fragment into an Efimov trimer, each of these, as the hyperradius goes off to infinity. And in the adiabatic approximation, or if you do the coupled channels, you find each of these wells holds 2 bound states, just as we said. The deeper of them is around 4.5 times as deep as the trimer energy for each of them, which you can kind of understand because there are 4 triangles in a tetramer, and if the key entity that binds the tetramer together are these sort of 3-body combinations into Efimov states, then it would be kind of plausible qualitatively that this number would be around 4 times as deep. And that is what we find numerically. What this means is, as you move along this axis and are making the 2-body Hamiltonian more and more attractive, before you get to that 3-body Efimov resonance, you should see these 2 4-body resonances. And I suppose I had, oh, that's right, I did this thing. Just one property about these is the 4 bodies obey the Efimov scaling. So as the Efimov size changes from one 3-body state to the next, the 4 bodies scale by this same Efimov factor of 22.7. And this is what the higher of the 2 4-body states looks like if you plot an isodensity surface, where here's the Efimov trimer is already a pretty large system compared to the atomic sizes. There's a nodal surface, and then there's the main wave function is far out. This peanut is sort of where the smaller, the tetramer, the more attractive one is sitting. Okay, so this kind of gives this generalized Efimov plot where you have the 3-body energies and the 2 4-body states on each of them, and these crucial points that should have experimental implication. And one thing we noticed was that at this special point where something interesting should be happening in the 4-body physics, in fact, there was a discrepancy with the Grimm experiment on 3-body recombination. Again, in our hyperspherical picture, how would 4-body recombination look? Well, we would have one or more incident 4-body continuum states. There would be some non-adiabatic coupling, and then you would come out into one of these possible ways the system could recombine, either into a trimer or 2 dimers or 1 dimer and 2 free atoms. So we have these curves, we have the couplings, we can just calculate this once we've done that, although it was a lot of work to get the potential curves and couplings. And also the scattering theory itself was a bit of a challenge. I am used in 2-body scattering to just looking up the formulas for cross-sections in terms of the S matrix. And we found there were no such formulas that we could find for like 4 bodies in the continuum simultaneously colliding. So we had a PRL about a year ago that derived the rate coefficient in terms of the scattering matrix that we calculate in these coupled channels. And it involves gamma functions and all that fun stuff theorists love. We also, in that same paper, we give, from a Landau-Zener type analysis, a simplified formula that could be used by experimentalists in practice. And this is just a test against our full numerics that shows it captures most of the right physics. Okay. So let me show you. This is the graph I mentioned that comparing the 2006 Grimm experiment with a calculation that only includes 3-body recombination. And you see there's this region of discrepancy. And after we had done this calculation and predicted these values, we noticed that this region of discrepancy is right there at 0.43 times the 3-body resonance state, right where a 4-body resonance is expected. And there was even some hint of maybe something going on at a second point slightly below the three-body resonance. So when we put all the machinery together and did the calculation of including four-body recombination, assuming the experiment was not measuring only three-body loss, but also had some four-body loss, according to this sort of a formula, we obtained this result. At different temperatures, you see, it seems to capture the right physics. Well, no, actually, we took the density the experimentalists estimated to be their peak density. That wasn't adjusted, but we did have one adjustable parameter of the strength of the coupling to a deep state, a deep hyperspherical channel. So there is that, but up above this resonance, these values are not sensitive to that. So these are pretty much model-free in this region, predictions. But the strength of this resonance, we had to tune with a parameter in our Hamiltonian. So the Grimm group was fairly excited when we showed them this prediction, and they went back and remeasured and found they could carefully extract the four-body and separate it from the three-body loss. And at those special points, minus 400 in scattering length and minus 750, they saw, in fact, that there are resonant enhancements of just the four-body loss. So this was a confirmation of our prediction. And these are big molecules we're talking about, these resonant states, 200 to 400 nanometers. Even though at those large distances, the particles feel no forces on each other at all, which is kind of amazing. Since then, there have been other experiments, this one by Randy Hewlett's group. They also see the minima and confirm the Efimov factor scaling between them. And they saw more than one three-body resonance, and they saw the four-body resonance, again, rather accurately where this universal prediction gives. Also, our calculation of the four-body rate agrees. There's a lot of spread in the data. There are many orders of magnitude, I think 12 across this vertical axis. But it's in reasonable agreement with our zero-temperature theory up until you get to the unitarity limit for our theory. And that seems to be about where the experiment saturates. These are just some checks in the experiment. I think maybe I'm running a little short on time. So let me just say a few words about the prospect of extending some of these ideas to more clusters, more than four particles. Javier von Stecker, after he finished his PhD, he wrote this year a nice paper on looking at not only 3 and 4 boson systems, but going to 5, 6, 7, 8, all the way up to 13. And he found that there is a simple universal scaling that once you know the three-body, where scattering length, where that Efimov resonance would occur, you could not only predict the four-body in agreement with our previous work, but also the 5, you could predict all of these. Everything seems to be controlled once you know the three-body Hamiltonian and where that first Efimov state is. That's enough information to predict this whole series, as far as we know, at least up to 13, which is as far as he calculated. There's no experimental evidence for these higher ones, but I think it will be exciting if the experiments can get to the point where they could see a 5-body recombination resonance, or 6, or something like that. And these are just the table of the scattering lengths where you would expect to see them relating the n-body scattering length resonance to the n-1 body. So with that, I think I'm presented the main bulk of what I wanted to say. The main result is that in this universality region, there's strong now both theory and experimental evidence of these four-body universal states. And the famous experiment in 2006 that saw three-body resonance actually saw a four-body resonance also, and has additional confirmation that that single resonance they saw was really an Efimov state. There's always the worry, if you only see one resonance, that maybe it was from some other mechanism. But I think this is very strong confirmation that it really was an Efimov state, since the four-body physics is matching it. You have the universal four-body states, and no, you don't need any extra parameter to predict where they are. It's fixed by the three-body physics. And so it really is an exciting time for this field. Thanks for listening.
So, does this, in the large N body limits, can you interpret these N body resonances as some kind of rubber many-body effect?
As a many-body effect of some other sort of many-body effect? Well, I'm not aware of any other sort of many-body effect that's known that would correlate with those. It's a pretty different kind of state, I guess. But it's an interesting question. We have had a few papers where we went to the infinite particle limit. It's pretty hard. Going 3 to 4, it's kind of growing exponentially in difficulty. But if you go to the infinite number limit, some simplifications happen. You can use Thomas Fermi approximations and get the potential curves in that limit. And we predict some interesting phenomena, like a collapse of a 3-component Fermi gas. That haven't been seen yet experimentally, but I'm still really curious to see if that'll hold up.
There was that special number of 1.0065, whatever.
Right.
Do they also appear in the four-body state? What are those?
Well, we don't have really an analytical theory for the four-body. That number comes, you can derive it in the zero-range limit. As Efimov did, you get a transcendental equation. It's a root of a transcendental equation that gives the index of that Bessel function, this -1 number. Yeah, I mean, we think our numerical evidence is that scaling factor is controlling the four-body scaling also. But so far, there's no analytic theory of four bodies the way Efimov had for three particles.
So do I understand correctly that real three-body forces would ruin the picture here?
Now, if they're short range, then they don't really ruin the picture. They set the scale. They tell you where is the first Efimov state, if you like. And then this universality applies only for the states that are reaching well beyond that range of the three-body and the four-body forces. Yeah, like, for instance, in this four-body calculation, we chose a three-body term that put the three-body resonance at the experimental location. And then we didn't do anything else that would change the position of the four-body resonances. And once we fixed the three-body, then the four-body came out right on top of the experiment. Yeah.
So what are the spin configuration for those three-body or four-body effects?
Well, these are all spinless bosons with total angular momentum 0.
So if the electron, what would that?
Well, first of all, electrons don't just have short-range interactions, so I'm not sure any of this maps onto electron physics at all. But to neutrons, neutron-rich nuclei, there should be some relevance. But yeah, you have to put in the Pauli antisymmetrization. That changes some things. For instance, it destroys the Efimov effect. If you had 3 neutrons, there is no Efimov effect, say, for 3 neutrons or three identical spin 1/2 fermions. But there would be if you had 3 different spin components, like a spin 3/2 nucleus. Zach?
Why is 3 the magic number? Why is 3 not even a 4-body parameter and 5-body parameter?
I guess I don't really know why. I mean, certainly it's clear this 1/r² potential has to have a cutoff. So it's absolutely clear you would need that for 3 bodies. Why that's enough, and it also settles everything for four bodies, it's not so clear.
You had a hand-wave curve. Efimov Effect occurs because two bodies are not bound, and we add one more, so we could have the same as before. Could you have a situation where three don't bind and four do?
Oh, absolutely. These resonances are in that regime. These resonances are before you have enough attraction to bind the three body. Yeah. So they're Borromean states in that sense.
So the one with the peanut going through the triangle, is that actually a dynamical system, or?
No, that's a bound state. It's a stationary state. Well, I should say the lowest would be a stationary state, but the higher ones, of course, they're embedded in continua of the other Efimov states below, and so they're truly speaking only resonances. We want to calculate the widths, but we haven't got the machinery to the point where we can do that yet. Yeah.
There are several atomic systems where they have been able to show that they can reduce it to dipole effect. So is it possible to see such physics in particle?
Well, actually, we're exploring that at the moment. There are some hints that three polar molecules would show an Efimov type effect, but it's very preliminary, and I don't think there's any paper on that I know of saying whether it's true or not. But yeah, it's a current question in the field, I'd say. Of course, polar molecules are of a lot of interest now in quantum gases for quantum information and so on. Yeah. There is no Efimov effect. I think you have to be more than 2.3 dimensions to have an Efimov effect. But there has been one predicted by a clever young fellow, Nishida, in mixed dimension systems. I don't know if you know this work, but where he has, I think the bosons are like moving in 2 dimensions and the fermions are in 3 dimensions, something like that. He predicts that there should be an Efimov effect for some weird case like that.
So on the technical side, do you still do these adiabatic bisector calculations, or are they full adiabatic states?
We normally use a DVR method that it's sort of in the spirit of the diabatic bisector method, but it's a much better technological way of handling that. It was invented by Tolstekin maybe 12, 13 years ago. He had a method. Because yeah, if you have really close avoided crossings, just doing the D by DR couplings is kind of a nightmare. So you usually want to have some way of diabetizing those potential curves and couplings.
Okay, let's thank Chris.
Thank you.